Good afternoon, everyone. Today we'll be taking a look at the Cambridge International AS and A-level chemistry exam. This is the paper 2, so this is the AS level structured questions from the May-June 2022 exam session that has just ended. Again, this is syllabus code 9701, component 22. Just some notes on the exam itself. You no longer have access to the data booklet. All constants and the periodic table is now included within the question paper itself. So that's something new. And for this series, the grade thresholds were set as follows. The exam itself is out of 60 marks. So A was around 32, a B 22, C 18, D 12, E 7. So they were pretty low thresholds this year. So if you were aiming for an A-star, I would say would be around 45 and above, maybe even 40. So moving forward, let's jump straight into the exam paper. It begins by saying magnesium has a melting point of 650 degrees C and high electrical conductivity. Explain these properties of magnesium by referring to its structure and bonding. So you need to make a reference to structure and bonding, and we need to comment on the high melting point as well as its high electrical conductivity. And this is a 2-mark question. So first thing, we need to be able to identify that there is a difference between the term structure and bonding. For magnesium, we can say that magnesium has a giant metallic structure with a metallic bonding. To explain the high melting point will be attributed to the strong metallic bonds within the structure. So strong metallic bonds accounts for the high melting point, and the high electrical conductivity is due to the presence of delocalized electrons that are free to move throughout the structure. So pretty straightforward. They say when magnesium is heated in air, magnesium oxide is the major product. Smaller amounts of magnesium nitride are also made. Calculate the oxidation number of magnesium and for the nitrogen species in magnesium nitride to complete table 1.1. So the oxidation number of magnesium in magnesium nitride, magnesium is a group 2 element, so its oxidation state will be +2. And in magnesium nitride, because we have 3 magnesium atoms, this will be 3 by 2, which is +6. So we need a charge of -6 to balance this. And we have 2 nitrogens, so the charge or the oxidation number rather in the nitrogen of the nitride will be -3. Identify the type of reaction which takes place between magnesium and nitrogen. Explain your answer. So this reaction should be obvious as a redox reaction, and the reasoning is because magnesium is losing 2 electrons, whereas nitrogen is gaining electrons. We can also appreciate or answer this question by saying that the magnesium is increasing its oxidation number from 0 to +2, and the nitrogen is decreasing its oxidation number from 0 to -3. Both of those things would be correct. Define enthalpy change of formation. This is a straightforward definition. It is the heat change when 1 mole of a compound is formed. Heat change when 1 mole of a compound is formed from its elements in their standard states. From its elements in their standard states. This is a straightforward definition that you should be able to recall. Now, this is a calculation question here. It says when 3.645 grams of magnesium burns in excess nitrogen to form magnesium nitride, 23.05 kilojoules of energy is released. So first things first, energy is released. So this tells us that the enthalpy change that we are dealing with will be negative because we are releasing energy. They asked us to calculate the enthalpy change of formation of magnesium nitride, showing your working. So to first approach this question, we should write a balance equation for the reaction that's unfolding. So magnesium is reacting with nitrogen to give magnesium nitride. So this should be balanced like this. So from this, we should be able to see now the enthalpy change of formation is defined as the heat change when 1 mole of a compound. So we have to work out for 1 mole of magnesium nitride. How much moles of magnesium do we have? So the number of moles of magnesium is given by the mass of magnesium, which is 3.645 divided by its relative atomic mass, which in the data booklet is 24.3. And this should give us 0.15 moles. So from this, our mole ratio of magnesium to magnesium nitride is 3 to 1. Therefore, the number of moles of magnesium nitride that we form, so the number of moles of magnesium nitride will be 0.15 divided by 3, which is 0.05 moles. And therefore, 0.05 moles of magnesium nitride resulted in a release of energy of 23.05 kilojoules. So to find for 1 mole of magnesium nitride, we would take our negative 23.05 divided by 0.05. And this should give us negative 461 kilojoules per mole. So this was a pretty straightforward question. Just need to take your time. Perhaps in this piece here, you need to calculate for 1 mole. So just be mindful of that. Question 2 deals with a group 2 element again. They say radium is an element found in group 2 of the periodic table. It is a crystalline solid at room temperature and conducts electricity. Radium chloride has a melting point of 900 degrees C and is soluble in water. Predict the lattice structure of radium chloride based on the properties described. So this should be pretty obvious that this is a giant ionic lattice. We should also be able to determine this from the fact that radium is a metal and chlorine is a non-metal. So together they would favor ionic bonding. 1 mark for that question. The question also continues, draw a dot cross diagram to show the arrangement of outer electrons in radium chloride. So radium is a group 2 element, so it's going to lose its 2 valence electrons and it will form a species with a charge of 2 plus, which we would expect like this. And chlorine is in group 7, so there are 7 valence electrons in chlorine. Therefore, a chlorine atom will require 1 electron. So the 2 electrons donated from radium will go to each chloride atom. So we should see something like this. If I let the X be an electron from chlorine and a dot an electron from radium, we should see something like this. And this will pick up a negative charge, and we would also have, we would just have 2 of this. Right, so we'll have 2 of this. So you can just put 2 of this, and this is your 1 mark for your question. Solid radium and calcium show similar reactions with water, but the reaction occur at different rates. Separate samples, each containing a single piece of solid radium or calcium, are added to equal volumes of cold water. Each sample contains equal numbers of moles of solid and the water is in excess. Construct an equation for the reaction of radium with water. So any group 2 metal will react with water to form the corresponding metal hydroxide and hydrogen gas. So radium will react with water to form radium hydroxide and hydrogen gas, and to balance this we need to put a 2 in front of the water. Right? So pretty straightforward. This should be straightforward recall from your notes. Identify which element, radium or calcium, reacts with water at a faster rate, and suggest how the observations of each reaction would differ. So notice the question is not asking for an explanation for why the rates differ, but for an observation. So we should know that radium is more reactive, so radium will react faster. And an observation that we should see is there's effervescence. There's more rapid effervescence with radium, so more rapid fizzing or effervescence. So effervescence or fizzing. Or you could also say that the radium will disappear more quickly. Disappears quicker. And now the question asks us to suggest why these reaction rates differ. And the reaction rates differ. What comes to my mind immediately is that radium has a lower ionization energy. So 1 point will be lower ionization energy for radium. And the reason why the ionization energy is lower is because of the greater atomic radius. So the valence electrons in radium experience more shielding or more screening, and this reduces the nuclear attraction. Right? So this reduces the nuclear attraction for the valence electrons, so they're easier to lose. Right? Reduced nuclear attraction. And this would explain why this explains why the reaction rates are different. Alternatively, what a student could say is that yes, the ionization energy is different, but this also leads to the activation energy of the reaction being different. And the radium will have, because of its lower activation energy that's required for the radium, you will have more effective collisions, or the proportion of particles with energy greater than the activation energy would be higher in the case of radium because of the reduced activation energy. So these are two possible paths one could take in attempting to answer this question. The question continues that one of the solutions is cloudy when the reaction has finished. At the end of the reaction, universal indicator is added to each reaction mixture. Suggest pH values of the solutions made in both reactions. Explain your answer. So radium will produce a solution of radium hydroxide, and calcium will produce a solution of calcium hydroxide. What we need to recall here is that the solubility of the group 2 hydroxides increase as the group is descended. So the solution that is cloudy when the reaction is finished is actually the calcium hydroxide solution. Now both solutions are going to have a pH greater than 7 because we have an alkaline solution. However, the pH of the radium hydroxide should be greater, so I would say approximately around pH 10 to 11. And the calcium hydroxide will be approximately pH 8 to 9. And the reasoning for this is because the radium hydroxide is more soluble, because the solubility of the group 2 hydroxides increase as you go down the group. So this was really testing the solubility of the hydroxides. All right. A sample of aqueous calcium halide, so this is a generic calcium halide, contains either chloride, bromide, or iodide ions. Complete table 2.1 to describe a two-step process that could be used to identify the halide ion present. So immediately off the bat, you should be thinking about using acidified silver nitrate. So acidified silver nitrate is our method. The acidified silver nitrate is really silver nitrate with nitric acid. The chloride ions will give a white precipitate. The bromide ions will give, it's described as cream or off-white. So you can say cream or off-white precipitate. And the iodide ions give a yellow precipitate. It's actually pale yellow. And to distinguish which halide ions we have, we should know that we have to add ammonia solution. So there are two ways we can do this. We can either add dilute ammonia solution or concentrated ammonia solution. So if we add concentrated ammonia solution, so ammonia aqueous, and I'm going to say concentrated, the white precipitate dissolves. So if it's chloride, the white precipitate will dissolve. If it's bromide, the precipitate will also dissolve in concentrated ammonia solution. And for the iodide, the precipitate remains insoluble. Right? The precipitate is insoluble, or you can say it does not dissolve. And this is true for dilute or concentrated ammonia solution. So again, if you use ammonia, if you use concentrated ammonia, with chloride, the precipitate dissolves. With bromide, the precipitate also dissolves. And with iodide, the precipitate will remain insoluble or does not dissolve. If we had used dilute ammonia solution instead, for the chloride ion, the precipitate will also dissolve. But with the bromide, the precipitate will partially dissolve. So in dilute ammonia, the bromide ion precipitate partially dissolves, and the iodide precipitate will also remain insoluble. Right? Now question 3 deals with the principles of chemical equilibrium. So the question tells us that 0.025 moles of hydrogen iodide is added to a closed vessel and left to reach dynamic equilibrium. The total pressure of the vessel is 100 kilopascals. And this is the equation for the dissociation given here. Explain what is meant by dynamic equilibrium. So this is again straightforward recall from notes. Dynamic equilibrium is such that the rate of the forward reaction is equal to the rate of the reverse reaction. That's one aspect of dynamic equilibrium. The other aspect of dynamic equilibrium is because these rates are equal, there is no change. There is no change in macroscopic properties of the system. So no change in macroscopic system properties. And what does this mean? If there's no change in microscopic system properties, it means that there is no change in measurable properties of the system and that the concentration of reactants and products remain the same. So that is implied from the statement macroscopic system properties are constant. Right? So there's no change in measurable properties of the system and the concentration of reactants and products will remain constant. They ask us to describe one difference in the initial appearance of the reaction mixture compared to the mixture at equilibrium. So initially, you would only have hydrogen iodide present, which is a colorless gas. And at equilibrium, we have hydrogen, hydrogen iodide, and iodine, which is in the gaseous phase. And we should know that iodine forms a purple vapor. So what really happened is that you will have a color change from colorless to purple due to the iodine vapor. Right? The question asks us here to write an expression for Kp for the reaction described in 1. So we know that any equilibrium constant is the product of concentration of the products divided by the product of concentration of the reactants. That's in case of Kc. For Kp, we write it in terms of partial pressures. So this would be equal to the partial pressure to the partial pressure of hydrogen by the partial pressure of iodine divided by the partial pressure of hydrogen iodide squared. Because the stoichiometric coefficient of hydrogen iodide is 2, so this becomes the exponent down here. And although the question doesn't ask for it, but the unit for Kp for this reaction is of course unitless because all the units cancel. Now the question says at equilibrium the partial pressure of hydrogen iodide is 86.4 kilopascals. Calculate the amount of hydrogen iodide gas present in the mixture at equilibrium. Show your working. So you are specified here to show your working. So to approach this question, what you need to remember is that partial pressure is proportional to mole fraction. Right? And we can signify mole fraction with Caie. Caie is also used to signify electronegativity. It could also be used to signify mole fraction here. So it's proportional to mole fraction. What is the partial pressure of the hydrogen iodide? It's 86.4 kilopascals. Earlier in the question, we were told that the total pressure of the system is 100 kilopascals. Therefore, the mole fraction of hydrogen iodide in the mixture, so we can write that the mole fraction of hydrogen iodide in the mixture is 86.4 divided by 100, which gives us 0.864 as our mole fraction of hydrogen iodide. What we need to work out now is the actual number of moles that we have at equilibrium. So if we begin here with our equation, 2HI is decomposing to give us H2 and I2. And they told us that initially we have 0.025 moles of hydrogen iodide, 0.025. So, and this is initially. So we will have 0 moles of hydrogen and 0 moles of iodine. At equilibrium, what happens? Let us assume X moles of hydrogen and iodine are produced. Because it's a 2 to 1 mole ratio, 2 moles of hydrogen iodide produce 1 mole of hydrogen. It implies that at equilibrium we have 0.025 minus 2x. And from this we can get the mole fraction of hydrogen iodide. The mole fraction of hydrogen iodide is 0.025 minus 2x all over the total number of moles which we have present, which will be 0.025 minus 2x, which just becomes 0.025. This is the expression for the mole fraction, and we know that our mole fraction must be equal to 0.864. Therefore, the amount of hydrogen iodide gas present is given by the numerator in our expression here. And all what we need to do is cross multiply, so 0.864 multiplied by 0.025, and this gives us 0.0216 moles. 0.0216. And that is the amount of hydrogen iodide present. So this question required us to know that mole fraction is proportional to partial pressure, and we just need to apply the concepts of equilibrium here, generate an expression for the mole fraction, and then we could calculate the amount of hydrogen iodide that was present at equilibrium, which we got to be 0.0216 moles. Right? This part of the question switches to energetics. They say use equation 1 and the bond energy values in table 3.1 to calculate the change in enthalpy delta H for the thermal decomposition of 1 mole of hydrogen iodide gas. Show your working. Notice what the question asks us for. 1 mole of hydrogen iodide gas. So we know what our equation is. Our equation is 2HI decomposing to give hydrogen and iodine. So a good way to work this out is that the energy change, delta H, is equal to the energy required to break bonds. So energy required to break bonds plus the energy given out when bonds are formed. When bonds form. So remember that bond breaking is an endothermic process. It requires energy. And bond forming is exothermic. So for this reaction, if we calculate the enthalpy change for this reaction as given, which is actually the equation for the decomposition of 2 moles of hydrogen iodide, we would calculate it as follows. The energy required to break the hydrogen iodide bond is 2 by 299, and this would be positive because we are bond breaking, plus the energy given out when bonds are formed. We form 1 mole of hydrogen, which is minus 436, and 1 mole of iodine, which is negative 151. And this works out to positive 11 kilojoules per mole. However, this positive 11 is for 2 moles of hydrogen iodide. The question asks for 1 mole, so we divide 11 by 2 and we will get positive 5.5 kilojoules per mole. So the trick in this question was really that they are asking us for 1 mole of hydrogen iodide gas. Describe the effect of increasing pressure on the value of Kp for the decomposition of hydrogen iodide. Pressure will have no effect in this case because the number of moles of gas on the left-hand side and right-hand side of the equation are the same. Notice we have 2 moles of hydrogen iodide and we have 1 mole of hydrogen, 1 mole of iodine. So 2 moles of gas on the left-hand side and 2 moles of gas on the right-hand side. So pressure will not affect this equilibrium. The question continues that HCl gas is prepared by adding sodium chloride to concentrated sulfuric acid. Hydrogen iodide gas is not prepared by adding sodium iodide to concentrated sulfuric acid because the hydrogen iodide produced also reacts with the concentrated H2SO4. Identify the type of reaction that occurs when sodium iodide reacts with concentrated sulfuric acid to form hydrogen iodide. So this is an acid-base reaction. This is an acid-base reaction, and it becomes apparent when we write the balanced chemical equation for the reaction, which in this case would be sodium iodide plus sulfuric acid to give sodium hydrogen sulfate plus hydrogen iodide. And this is an acid-base reaction. This is an acid, and we can think of the sodium iodide as a base. The question didn't ask you the equation, it just wants you to identify the type of reaction that occurred. Now the question continues, write an equation for the reaction of hydrogen iodide with concentrated sulfuric acid. So the hydrogen iodide is actually going to reduce the sulfuric acid to a sulfur-containing product. Now, for all the, well, I shouldn't say for all, but for HBr and HI, when they react with sulfuric acid, you will always form back the halogen, which in this case is I2, and you would always form water. What differs is the sulfur-containing product. If we had hydrogen bromide, we would have gotten sulfur dioxide as the sulfur-containing product. With hydrogen iodide, our sulfur-containing product in this case would be H2S. And to balance this equation, we would require 8Hi plus H2SO4 to give us 4I2 plus 4H2O and H2S. Apart from H2S, we could have also formed SO2. There will actually be some SO2 formation as well. And it is also possible to completely reduce the sulfur to elemental sulfur. So these are other 2 equations that can also occur. And the question asks us, explain why hydrogen iodide gas reacts with sulfuric acid whereas HCl does not. And the reason is simply because HI is a stronger reducing agent. HI is a stronger reducing agent. Is a stronger reducing agent than HCl. Right? And that's the explanation. Right, switching gears a little bit now. Now we enter some organic chemistry questions. They tell us here bromine reacts with butane in the presence of ultraviolet light to form bromobutane. Two structural isomers with molecular formula C4H9Br are produced during this reaction. Draw the two structural isomers and state the systematic name of each isomer. So this is a free radical substitution. It should be apparent to us that this is a free radical substitution. The structure of butane is, in skeletal formula, is this. This would be the structure of butane. When we are forming two structural isomers, so it is possible that one halogen atom is attached here, and the other isomer is a halogen atom attached to carbon 2. Oh, I drew this a little bit badly. Let me just draw this over. Will be a bromine atom attached to carbon 2. And this will, of course, be one bromobutane, and this will be two bromobutane. Identify the type of structural isomerism shown. These are positional isomers because the isomers only differ with respect to the position of the bromine atom on the carbon atom. This is bromine on carbon atom 1, this is bromine on carbon atom 2. So these are positional isomers. Halothane is an anesthetic. Identify the chiral center in halothane and mark it with an asterisk. So the chiral center is a carbon atom with 4 different groups attached. And this should be obvious that it is this carbon here. We have chlorine as one group, bromine as the other group, hydrogen as the other group, and this CF3 as the other group. When halothane reacts in ultraviolet light, homolytic fission occurs and the CBr bond is broken. Construct an equation to show the homolytic fission of halothane. So what they are saying is this bond, the CBr bond, is going to break homolytically. So mechanistically, we would see something like this. And what we are going to get in this process is the formation of 2 radicals. Homolytic fission results in the formation of radical species. So we will see CF3, CHBrCl to give us, the first obvious one is that we will get a bromine radical, which is signified by this dot, plus CF3, CHCl radical. Right? Pretty straightforward. Complete figure 4.2 to show the arrangement of electrons in a bromine atom using the electrons in boxes notation. So bromine is in the 4th period of the periodic table and it's a group 7 element. So we should know automatically that if it's group 7, it's going to have 7 valence electrons here. So the 4s and 4p orbitals should hold 7 electrons in total. And the 3d orbitals will be completely filled in the case of bromine because it's in the 4th period. So if we use our electron and box diagram, we will have our 10 electrons here, and I should really do them like this. According to Hund's rule, the electrons will fill singly and then pair. So for the 4s, we pair, and then for the 4p, they will fill singly and then we pair them up. And we need to have a total of 7. So this is 1, 2, 3, 4, 5, 6, 7. Right? And this would be the electron and box diagram for bromine. They tell us here X is an addition polymer. Draw the monomer of X. So it's an addition polymer. We should know that in addition polymerization, we go from a unsaturated compound to one that is less unsaturated, more saturated. So it usually involves the breaking of double bonds. This is the repeating unit itself. This is one individual repeating unit. So it should become apparent to us that our monomer is this. This is our monomer species here. And We can show this very easily because when we form our double bonds, one unit will just polymerize here. These are hydrogens, which are assumed here. Hydrogen, 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 and they will just form a next bond here. And this structure will just repeat. Right? The structure will just repeat over. So this is our monomer. So just one reason why the disposal of items made from X is difficult. You should know again from your notes that these addition polymers are non-biodegradable. They are non-biodegradable. And with this particular monomer, if we try to dispose of this, because we have chlorine in the monomer, it is possible that we can produce HCl. If this polymer is to be burnt or disposed, we can produce HCl, which is toxic. So these are the reasons why disposal of this particular polymer will be difficult. Right? Our next organic question, figure 5.1 shows 3 reactions of 2-bromopropane. So we have reaction 1, we are forming an alcohol in this reaction. Reaction 2, we are forming an amine. Reaction 3, we are forming an alkene. Complete table 5 for each reaction by stating the reagent and conditions used, identifying the type of reaction that occurs. So in reaction 1, we have a haloalkane, which is the 2-bromopropane, and this is being converted to an alcohol. So this should immediately think of us to some sort of SN1, SN2 type mechanism. This is a hydrolysis, and the reagents we would use for this is aqueous sodium hydroxide. So sodium hydroxide aqueous with heat. And the type of reaction here, it's a substitution. We are substituting the bromine for OH, so you can say substitution. If you want to be more specific, we can say it's nucleophilic substitution. Reaction 2 is the halogenoalkane being converted to an amine. So for that reaction, we should be aware that we need to use ethanolic ammonia. So ethanolic ammonia, which is just ammonia in ethanol, and this reaction has to be heated under pressure. And the reaction is also the same as above. It is a nucleophilic substitution. And in the third reaction, we are going from a haloalkane to an alkene. So this immediately should tell us that we are dealing with ethanolic sodium hydroxide. So this is ethanolic sodium hydroxide, which means sodium hydroxide in ethanol, and we heat. And this is actually going to give us an elimination reaction. All right, so pretty straightforward. The question continues here. A sample of 2-iodopropane reacts under the same conditions as reaction 1 to produce the alcohol shown. Explain why 2-iodopropane reacts at a faster rate than 2-bromopropane. And the reason is simply because the Ci bond is weaker. The Ci bond weaker than the CBr bond. And what this in turn implies is that the activation energy of the reaction is less. And this is for the case of the iodine compound. So because the Ci bond is weaker, it means the bond breaks more readily, and this in turn reduces the activation energy of the reaction, so the hydrolysis occurs faster. Right, they tell us here now, figure 5.2 shows how butan-1-ol can be made from 1-bromopropane in 3 steps. In step 1, 1-bromopropane reacts with cyanide to form butane nitrile. Complete figure 5.3 to show the mechanism for step 1. Include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. So the bromine is being replaced for the cyanide group. So this should tune us in that this is some sort of substitution, and it should be a nucleophilic substitution since the carbon of the nitrile is negatively charged. So if we have to include our dipoles, we should recognize that the carbon that bears the bromine is going to be delta positive, the bromine is going to be delta negative. So this carbon is our electrophilic center. The carbon of the nitrile is going to be the attacking group. It's negatively charged, which implies that there's a lone pair of electrons here. And this is going to attack the carbon atom, and then this bond is going to break. And these arrows are full arrows to show that it is heterolytic fission that's taking place. And this will lead to the butane nitrile and bromide ion. It is important that you have your dipoles and the attack is correct. And you show the arrows always go from where you have electrons to where you don't have electrons. So from our carbon of the nitrile to the electrophilic carbon center, and then the CBr bond heterolytically breaks to yield the product. Right? The question says that in step 2, butane nitrile is heated with HCl. A hydrolysis reaction occurs. Construct an equation for the reaction in step 2. So they tell us that we are heated with HCl and a hydrolysis reaction occurs. So for hydrolysis, a key reactant is water. Because it's hydrolysis, we need water. So the equation for this reaction, for butane nitrile, if we look at the structure of butane nitrile, which is this, we have Cn, CH2, CH3. They're telling us it's reacting with HCl, and we also need water because it's a hydrolysis. And this will give us, if we look at the structure up here, this is going to give us this is going to give us butanoic acid. This is going to give us butanoic acid, which is CH3, CH22, CO2H, plus what could be the possible other product? We have nitrogen and we have HCl, so it should be feasible to think that we are also going to get ammonium chloride as a byproduct here. And so this is our equation for the reaction. To balance this, we would need 2 moles of water. And this is our balance equation for the reaction. They tell us that step 3 is a reduction. So it's a reduction of the carboxylic acid, the COOH group, to a primary alcohol. Construct an equation for the reduction in step 3. Use H to represent 1 atom of hydrogen from the reducing agent. So in this case, we have the butanoic acid, CH3, CH22, CO2H, and it's reacting with hydrogen from the reducing agent, and we are going to get a primary alcohol, which in this case would be CH3, CH2, 3OH plus water. And to balance this equation, we would include a 4 in front of the hydrogen. And then the question asks us to identify a suitable reducing agent. So this is the reduction of a carboxylic acid directly to a primary alcohol. So for this, a suitable reducing agent will be lithium tetrahydroaluminate 3, which is LiAlH4, and it's actually in dry ether. You don't want any moisture. So it's LiAlH4 in dry ether. That is the reducing agent we would use. Right, and now we come on to the last question of the paper. It tells us Z is a molecule which contains the elements carbon, hydrogen, and oxygen only. Z contains only alkene and carboxyl functional groups. Complete table 1 by describing the observations that occur when 2 different reagents are added to separate samples of Z. So if we add bromine to Z, because we have an alkene group, it will undergo an addition reaction here, so the bromine will be decolorized. So the orange color of the bromine, so it's brown orange, so you can say bromine decolorized, Br2 decolorized, or orange color disappears. And for sodium carbonate, the sodium carbonate will react with the carboxylic group. We will get fizzing or effervescence. So fizzing, or you can say effervescence. Right? The question tells us here, table 6.2 shows the percentage by mass of each element present in Z. Use the table to demonstrate that the empirical formula of Z is CHO. Show your working. So they want us to know the empirical formula, which is the simplest whole number ratio. So how to begin this question? We would say carbon, hydrogen, oxygen. The percentage by mass is 41.38, 3.45, and 55.17. The first step is to divide by the relative atomic mass of each element. So this is division by 12 for carbon, division by 1 for hydrogen, division by 16 for oxygen. And this will give us 3.45, 3.45, 3.45. And then we divide by the smallest number that we get in this step here. And all the numbers are the same, so we divide by 3.45 and we get 1, 1, 1. And this is our empirical formula, C1H1O1, which implies CHO. Pretty straightforward question, only 1 mark for this. Right, figure 6.1 shows the mass spectrum of Z. They tell us here, deduce the molecular formula of Z. Explain your answer by referring to the molecular ion peak in 6.1 and the empirical formula of Z. So the first thing is to determine what is the molecular ion peak. This peak here at 116 should tell us that this is the molecular ion peak. We know that it's also the molecular ion peak because we have the M+1 peak at 117. So this peak comes 1 atomic mass unit higher, which is due to the presence of the carbon-13 isotope. So the atomic mass, the relative atomic mass of the compound is 116. Now we know that the empirical formula is CHO. If we add up these units, 12 plus 1 plus 16, we would get 29. And if we take 116 divided by 29, we get 4. Therefore, we know that the molecular formula of Z is C4H4O4. Good. And then the question tells us, use figure 6.1 to suggest the formulae of the fragments with Me peaks 45 and at 71, and then suggest the structure of Z using relevant information from tables 6.1, B, and C. So what could these possible fragments be? Now we need to go back to what the question had told us. The question told us we have only an alkene and a carboxylic acid group. So it perhaps might be simpler if we suggest the structure of Z first and then work backwards to see if our suggestion is correct. Because we only have acid and alkene groups, it means that the end has to be an acid group. Now notice this piece of the molecule uses COOH. Our molecular formula tells us that we have 4 oxygens. So it is conceivable that we have another acid group on the other end of the molecule. So this is 1, 2, 3, 4 COOH. This accounts for the C4 and the O4. And because we also have an alkene, the only place where that double bond could go is between carbons 2 and 3. So we can use the reasoning as discussed to deduce the structure as is. Another thing to be mindful of is that because of this double bond, we have drawn the trans isomer here. Alternatively, you could produce or draw the cis isomer, which would look something like this. We would have a cis isomer, which would look like this. O, OH, O, OH. Right? We can also have drawn the cis isomer. Now using this, we can now suggest what these fragments are. If we look at the carboxylic acid group, we can fragment the molecule in this piece here, and we'll get this carbon, these two oxygens and hydrogens. So we can get CO2H plus, right? CO2H plus. And this would add to the 45 Me ratio that we have. And then at 71, what we do is we fragment at this piece, because 71 is really 116 minus 45, which means we are losing the carboxylic group from the other end. And this fragment will therefore be C3H3O2 plus. So that is one way to riddle out this question. You could have actually suggested the structure first and then work out what the fragments were. Or you could, from careful deduction, realize that the Me fragment at 45 is a carboxylic group. And at 71, 71 is 116 minus 45, which means we are losing a carboxylic group from the other end of the molecule. And this would have given us the structure shown here. So you can either draw the trans or the cis isomer. And this was the end of the paper. It was a pretty straightforward paper. Some little subtleties here and there that could have thrown you off, but once you took your time, the paper should have been very manageable. I hope that this paper and this work through was useful to some of you all, and that some of the questions are now a little bit clearer. So thank you for watching, and until next time.